All right, so how do we determine how much these numbers in our objective function can actually change so that we'll actually get to the same optimal decision? Again, keep in mind when these numbers change, the profit will change, but the decision doesn't have to change. So that's what we're looking for. So how much can the numbers in our objective function be changed, which will lead us to the same decision, in this case, the same decision to produce only the finished grade number. So again, what we're doing is graphically, we're thinking of our feasible region, and we have our line that's representing our objective function with our maximum profit, based on the fact that the finished grade lumber has a profit of $120 per 1,000 board feet, and the construction grade lumber has $100 profit per 1,000 board feet. So our profit function is just this line here, and I'm going to call it in the notes this little lowercase l. So we can think of our profit equation by introducing some variables here. And this like triangle looking Greek letter delta is just general mathematical use for change. So it's representing a change in something. So delta with the subscript f is going to be our allowable change for our profit for the finished grade lumber. Basically, how much can that number change and still lead us to the same decision. And then delta with the subscript of c is how much the construction grade profit can change and still lead us to the same decision. We saw in the last video that changing these numbers can change the slope of our objective function line, and that quite often leads to the same decision. But if that slope is changed enough, then a new decision will have to be made to be optimal. So all we think of is putting these variables into our line. So instead of having $120 profit, we have 120 plus this change, which we're trying to figure out what that is. And instead of the $100 profit for the construction grade, we think of it as 100 plus some amount of change. And as those numbers, delta F and delta C, change, that's just what I'm doing in the graph over here when we change the numbers of C1 and C2 in our objective function. I'm changing the value, I'm changing the slope by changing one of the numbers, or both of the numbers. So if they both change, we still obtain the same decision, but if they change enough, then we no longer have the same decision. We will have to make a new decision, as this picture illustrates. So basically, how much can this slope of our line change? In a two-variable problem, this is very simple, because you can basically look at a picture to see what's happening and do some simple algebra to determine how these two numbers can both change simultaneously to lead to the same decision. So in this example, it's quite simple. Since our decision is occurring at this vertex of our feasible region, the allowable change corresponds to any changes which change the slope of this line to make it less steep. In this case, moving this way makes it less steep until it would get parallel with one of the edges of our feasible set, which contain our original decision. So we can decrease the slope until it gets to this point here. At that point, if we go any further, a new decision will have to be made. But we can also increase the slope, in this case, in various ways. In particular, if we change this one, it gets steeper, and that causes an increase in profit. In this case, off the scale here, make it a little bit less. But if I increase the slope, and what I mean by that is the slope of this line is negative, so making it more steep is actually decreasing the slope. It's making it a larger negative number. So we want to know how much can we change it. In this example, making this line steeper and steeper will never change the decision. And the reason for this is our vertex 0.40 is only on one edge that can really be accessed by this line. And when we get to other problems, we'll see our vertex could be on two edges which are not the axes in this case. Like we have one side of our triangle is the vertical axis and the other side is a horizontal axis. In this case, because we're maximizing our objective function, we're not going to be deciding on 0 of either product. So we really only have one choice here. Basically, just to know how much can the slope be moved closer and closer to the slope of one side of our triangle containing the 0.40 so that the line of the objective function will still go through the 0.40. So from an algebraic point of view, we just want to look at what is the slope of this profit for a general value of delta f and delta c. Well, it's just a line. So if you solve this equation for y, what is the slope going to be? We're going to have to subtract the x term to the other side, so it'll have a minus sign in front of it. And then we have to divide everything by 100 plus delta c, because that will give us the slope. We'll get an equation, y equals like mx plus sum b, where m is the slope. So what's that slope? It's this number here in the lower left-hand corner. So the slope of our generalized profit equation with our allowable changes in place is just negative 120 plus delta f divided by 100 plus delta c. So as those numbers delta f and delta c change, the slope of that line changes. So what do we want to know? We want to keep that slope, in this case, less than or equal to the slope of the top edge of our triangle. Because both of those slopes are negative, and a steeper negative slope is a smaller number. So once our slope of our line becomes greater than the slope of this edge, that will cause a new decision to occur. And on the other hand, decreasing the slope of this line, making it more steep in this case, means we will always have the same decision. So there's no limit on the other end. So in this case, we only have one inequality. In general problems, we'll see you'll have two inequalities for a two-variable problem. And when we get to multivariable problems with three or more variables, this gets a little more complicated, and you can actually write a program to determine inequalities based on what you do with the simplex method. The idea there is, in your simplex method, instead of putting in the numbers for your profit, you put in abstract variables, and then you perform the same steps that you would have to solve the problem, and then you see from those steps what those numbers would have to be limited to in order to lead to the same decision. But in higher variable problems, we're not going to necessarily need to do that. We're going to focus on just individual changes, one number at a time, because that already gives you an idea of the sensitivity of a problem. But in these two variable problems, we can actually find a single or two inequalities involving both of these numbers, delta f and delta c, to see how they are related and how changing both of them can lead to the same decision. So in this problem, since there's only one edge of our feasible set that our objective line could really be parallel to, we just want to compare it to the slope of that edge. So it's negative 120 plus delta f divided by 100 delta c. It's the slope of our line. As we change delta f and delta c, in order to keep the same decision, we need that slope to be less than or equal to the slope of the edge of the top part of this triangle, which we go back to our original problem, is our first inequality, 2x plus 5y less than or equal to 8. So again, the equation that's describing that edge is 2x plus 5y equals 8. Solving for y, the slope is going to be y equals negative 2/5 x. And I don't care what the other stuff is. I just care about the slope. So slope of the line being described here is negative 2/5. So the slope of our generalized objective function, we need it to be less than or equal to negative 2/5. As long as that occurs, we will make the same decision, being choosing 4,000 board feet of finished grade lumber to produce and 0 board feet of the construction grade lumber to produce. Once the slope of our objective line becomes greater than this negative 2/5, we would have to then make a new decision. So all we do is we have an inequality, and we can just kind of solve this inequality algebraically to relate the two allowable changes. And we get what we have on the right. So as long as the change of our profit per 1,000 board feet of finished grade lumber, as long as that number stays greater than or equal to negative 80 plus 2/5 times the change in profit per 1,000 board feet of the construction grade lumber, we will use the same decision. So again, in two-variable problems, we can actually relate the two variables quite easily because it's just a simple algebraic observation. Just taking the slope of our profit line and comparing it to the slopes of any edges that are next to, or any edge in which our solution is actually on. Now again, in this case, the other edge that it's on is the line y equals 0. So 0 slope. But changing our profit, these numbers C1 and C2 are going to be positive in general, so we don't really have to go the other way. Now it could be in real life that you were making hundreds of different products and some product could actually become less profitable, and you still might want to decide to make some of them because problems are complicated and all these variables are interrelated. So it is possible things like that could happen. But for us, we'll just keep it simple for now. And just realize that in this case, we really only have one edge of our feasible set to compare the slope of our line to. In this case, we get the relationship delta F has to be greater than or equal to negative 80 plus 2/5 delta C. So if delta F and delta C are numbers that satisfy that inequality, we know that the same decision will be optimal. The only thing that will change is how we compute our profit.